So thank you for joining me to listen my monologue lecture 6.3 regarding the electromagnetic theory behind the phenomena of reflection and refraction. So what I will be doing here in this lecture is that I will essentially derive Snell's law and the law of reflection by just using the Maxwell's equations and the boundary conditions that are associated with an interface between two dielectric medium. So this is what I will be doing, and I like it very much because this gives me a very firm grounding in the follow-up treatment, so that we really know that everything can be tracked all the way down into the Maxwell's equations. So what we do here is that we will look into this situation that we have processes of reflection and refraction, and we want to understand more rigorously what happens in order to really quantify the portion of light, for example, that is being reflected and or transmitted at the same time. So essentially, this also provides us means to calculate the Fresnel coefficients that we will be speaking about in the next lecture. So let's first derive the laws of reflection and refraction, and this we will do by just using the electromagnetic field theory. So basically the Maxwell's equations. So we start by just looking at the field EI, so that would be the incident field, and we assume that it's a time harmonic plane wave propagating along a wave vector direction of Ki, and that the refractive indices of the two media of interest are still Ni and Nt, so that the top medium is associated with the refractive index of Ni, and the lower medium is associated with Nt refractive index. And of course, we assume implicitly that the Ni is smaller in value than Nt, so that the picture makes sense. The transmitted ray actually bends towards the surface normal. And the surface, we need to somehow define that. So let's just say that would be the plane where z coordinate equals b, and then we define the surface normal to be n hat. So this is the situation problem at hand, and we now tackle solving these based on the Maxwell's equations. So let's label the reflected and the transmitted fields as ER and ET respectively, so that the ER as in reflected and ET as transmitted. And let's now plug in the kind of explicit equations that describe these three plane waves of interest. So that the incident field is of a form that we have the polarization AI vector, and then we have the time harmonic plane wave component, the phase term there, so that we have the exponent I, Ki, R minus omega I, T. And for a case of generality, let's also just allow us a possibility that the frequencies of these different components also could be changed. And we will see later on that, of course, in processes of reflection and refraction, the angular frequency of light is not being changed, but nevertheless, let's for the sake of generality, keep the notation absolutely clear. So, and this is the refracted field, so ER equals in the same kind of form. And now, just like I said, please note here that for the sake of generality, we allow in principle in the derivation that the frequencies of these different plane wave components could be different. So please note omega I, omega T, and omega R here. And here, of course, we have the KT, Ki, and Kr, the corresponding wave vectors associated with these three plane wave components. So this is a general treatment, and fields can propagate along any direction. So essentially these Ki, Kr, and Kt, they do not need to be of same vectors, and this is of course the case. And then we also allow the possibility that all these different field components can oscillate at different frequencies, so that omega I is not omega R and not omega T, at least in the beginning. Of course, we will realize at the end that they will be the same frequencies, but let's just see that to be the case and derive that to be the case here. And what we will do is that we will be deriving a so-called continuity equations or boundary equations that are associated with an incident field hitting an interface of two different dielectric media. So let's now derive these continuity equations for the incident electric field, because that will be very useful when we are taking use of the Fresnel coefficients and defining them. And we start here from the Maxwell-Faraday equation. So let's look in the differential form. How did the Maxwell-Faraday equation look like? So we had the curl of an electric field E, and this is equal to minus time derivative of the B field, like this. And this we can now simplify by just using the Kelvin-Stokes theorem. And of course, the Kelvin-Stokes theorem says to us that when we look at the Maxwell-Faraday equation in an integral form, so now looking at this kind of picture, essentially we're not using the differential form anymore, that we're looking at things on a kind of a little bit different scope, so that we are having a line integral over a given enclosed line defined with dou S, and now we calculate the integral of E with the line infinitesimal differential dl. And this, based on the Kelvin-Stokes theorem, says that this is the same as minus area integral over the S of dou B per dou T, so the time derivative of the magnetic field. And now we take the dot product of the S hat term here, so essentially it's the surface normal of this surface of interest, and then we have the differential area of interest. So essentially S is our area here enclosed inside this enclosing line defined with the dou S, and here we are looking at the Maxwell-Faraday equation in this kind of area in the plane of incidence. So essentially Maxwell-Faraday equation applied in integral form, and then we apply the Kelvin-Stokes theorem into this problem because we had the curl of E being something, so we changed that to be the line integral. Here we assume that the surface S is small rectangle that intersects the interface, and S is the surface normal, S hat is the surface normal, and path known as the dou S is essentially those lengths that we describe here, so the different lengths of the path. So L1 is defined here or shown here, L2 here, L3 here, and L4 here. And this essentially dou S is the edge of the surface. That's a good word for it, edge of the surface S. Now what we do here, and please note that these L's, they are vectors in a way, so that they actually have a given direction, so that we here are propagating over the edge in a clockwise manner. So we shorten the edges L1 and L3, and now what happens is that the interface becomes, or the area actually becomes smaller. So this is essentially what happens. So we are shortening L1 and L3. So these are the lines that are going through the interface. And now our surface S is becoming shorter and shorter. So essentially the area of S tends to 0 in the case, and mathematically speaking, we would say that we take the limiting value of S surface and we let L1 and L3 to approach 0. And this means that then the limiting value of the area S will be 0 also. And now this is nice because that gives us a tools to look into the integral that we had wrote down into the previous slide. So the right-hand side of the surface integral's integrand. The integrand would of course be what was inside the integral, that we had take the partial time derivative of the B field times the dot product of the S hat. So this is the surface normal, and this remains of course finite, and then this turns the equation into a case that the line integral of E is 0. So this is what happens, so that when we take the limit of the surface area S becoming 0, this doesn't go to 0, and then what's left is that then this integral must tend to 0, otherwise we would be in trouble. And now this reduces into a case we can separate the integral into the cases that are left, so that then this equality holds. So essentially now that we are letting L1 and L3 to tend to 0, so that this rectangle becomes very small here. And now we are calculating the line integral over the dou S, and now the L1 and L3 integrals essentially vanish, and what's left is the line integrals over L2 and L4. And these guys are now what are left. And this takes place when L1 and L3 tends to 0. And now the surface area S is small. Please recall the limiting value is that it also should be 0 in the limiting case. And this implies to us that the fields that we consider, they are also constant valued in the plane and in the locations of interest. So mathematically speaking, now I could write that the field in every location on the line L2, we can write it that it's the total field in there is the incident field plus the reflected field. And then this is a constant valued field. And then similarly that the field in the line L4 is essentially a constant field. And essentially, since we're inside the medium, we just need to take use of the transmitted field. So physically, of course, like let me put in the parentheses first, and then I will look. So basically here, I want to know what kind of field I place into this integral. And since I'm dealing with a small volume, I can really make this very small also with respect to the x and y coordinates, so that the L2 can also be very small. I can then say that yes, this field, the incident field plus the reflected field in here will be actually a constant field. And the same thing applies also on the lower medium, so that when the volume of interest or the area of interest is small enough, then I can just state that when I'm performing this line integral, and then I should be knowing how this field evolves, I can just say that in every point on the line L4, it's a constant valued field, and this is denoted with the transmitted field ET. And now we also note that for the case of having a rectangle, and this is why we should always be lazy or smart in terms of defining what kind of systems we are solving, so that the length of L2 is equal to the L4, so we can simplify our notation that we just write that the length is L, and now we can actually estimate the above integral. And we will do that in the next slide. So what we can do is that we can now actually combine these relations together, and the integral now is being simplified quite considerably. So now we take the constant valued field out, since they did not vary with respect to the line integration. And then we have the t hat here. So this is essentially the unit vector, since we have the hat. And this is a unit vector pointing along an arbitrary direction along the interface, since this was essentially where we were integrating. And then what we're left is that we are left with the line integral L2, and maybe I should have just used L here. But this is essentially what's left of the former integral, the first term there, since we had a constant valued field. And now the same thing is being done for the second part, and now we take the transmitted field to be away. We take it out from the integral, and we calculate the dot product with the t hat, unit vector pointing along the arbitrary direction along the interface, and then we are left with the line integral that looks very solvable. So essentially these integrals now give me the lengths of L, and then I'm left with the two simple algebraic terms. So I have the fields multiplying with t hat times L, and then I have the other term minus E with the dot product with the t hat times L. And this is again still 0, since this was the condition we started with the integration. So here t is the unit vector pointing along an arbitrary direction along the interface. So this is essentially generalizing the case that we were considering the rectangle in a given plane of incidence, but of course we could define that plane of incidence could be in a way any direction along the plane. So we should generalize our notion of S here into a t. And essentially now the t hat is in the same direction as L2, and it's in a kind of opposite direction from the L4. So this is what gives me the right signs for the different terms. And this equality now gives me a condition, so I can just really look into these two equations, and I can reduce these to vanish the L from here, since it's in both terms. And now it gives me a condition that the incident field EI plus the reflected field ER dot product with the t hat equals the transmitted field ET with the dot product of t hat. And this must hold for all unit vectors of t we can imagine that are pointing along the surface S somewhere. And what this implies to us, like please now this is the t is really a vector pointing along the plane of interface. that this implies that all the tangential components of the electric field are in fact continuous. So this is now that we are able to actually put some physics around the mathematics that we have dealt so far. So basically, I have these two dot products, and the equality must hold for all the possible fields I can imagine. And since I'm taking the dot product with a field that is along the plane of interface, I'm basically looking at the tangential components of the electric field. And since this equality holds for all the components I can imagine, so that the EI, ER components, the tangential components are equal to the transmitted field's tangential components, I can actually say this to be the case. So I can really take some physics out of this quite mathematical looking equation. And I'm just basically taking use of the geometric interpretation of a dot product. Nothing more, nothing less here. And this is nice, because now we really have derived a boundary condition or a continuity equation that we have at hand. And this is more often not written using the dot product and t, but rather the surface normal n, because most of the time this is a quantity that is somehow more easily defined for a interface and a plane, so that rather instead of like defining many arbitrary t's, we actually define a single normal surface normal vector, so that in a way this is more convenient most of the time mathematically. And basically the previous equation, how it looks like when you write things with respect to the surface normal, is that now we must take the vector product. So we take the cross product with the with the EI and ER fields, and this must be equal to the cross product of the ET with the n hat surface normal. So essentially this equality must also hold. So instead of writing with the dot product of t, we can also state that this should be the case. So essentially, okay, let me write out the other parts and then explain a little bit how this is the case. So essentially, I can take the right-hand side of the equality and I can put it on the left-hand side. So what is left is that I have the incident field plus the reflected field minus the transmitted field, and I take the vector product with the surface normal, and this must be a zero vector. So essentially, this guy says to us that there's all points that are on the interface defined as the surface z equals b. When we take these points along the surface normal, because otherwise the vector product would give me a zero. So this is what it says to us, and it gives us this kind of continuity equation. And this, of course, this should hold for all points r on the surface that we have defined, and it should also hold at all instances of time. Please remember we are considering time harmonic fields with the time dependence of exponent I omega t here, so that we can write that in fact this above continuity equation to hold, we must look into the phase terms, the exponentials, and they must be equal at all times and in all locations of r that are on the surface. So that we are actually left with a quite stringent condition for the incident field and for the reflected field and the transmitted field. And this is essentially arising from the boundary conditions and the continuity equations. So one way of saying it was that we had that the tangential components of the electric field are continuous, and another way of looking at it is that we write it this way, and then we are almost done in terms of derivation of the reflection and refraction laws. So since we should have this physics working out for all possible occasions of time, what this implies that the frequencies of the waves must be equal, so that the omega I must be equal to omega r and omega t. So essentially, why this is the case is that this equality must hold at all times, so that I can have the time equals 0 here, or I can have the time equals 10 femtoseconds or 50 or whatnot. So if omega I, omega r, and omega t would not be identical to each other, then this equality would not hold if I'm not touching r here at all. So this is to what it boils down to, so that the frequency of light is not being changed under these processes of reflection and refraction. And now what we can also do is that then we can also think that this condition must apply at every point of r, and we can just let time t being 0, and this point r is essentially on the surface defined with the z equals b. And now that gives me equality that ki dot product with the r must be equal with the dot products of the kr and kt respectively with the r. And here we have 3 equalities. Let's now look at the first equality, and what this gives us is that we have a condition that we have ki minus kr dot product with r must be equal to 0. So essentially I'm taking the first equality and I'm taking the right hand side, moving that on the left hand side and taking r to be a common product, and now this is what is left. And this basically implies to me that this vector that is inside the parenthesis, this ki minus kr, these points along a surface normal n, because otherwise the dot product with r that is pointing along the interface is would not be 0. So ki, kr, and k, they had n, so this is the surface normal. They are essentially in the same plane, and this is way how do we define a plane of incidence, by the way. And this is quite nice. And this is essentially like a rising from here, that we have ki minus kr dot product with the r, and this was in the plane, and if the dot product gives me always 0, then this implies that this vector must point along the surface normal, so that otherwise it wouldn't be, this would not be possible, and then it implies that these all are actually in the same plane. And now let's look at the geometric interpretation of the cross product, the vector product, and this equation above also implies to us that if we take the cross product with the surface normal n hat with these 2 vectors ki minus kr, then this should be a 0 vector. Because like if this vector ki minus kr points along the surface normal n, if I take the cross product with the surface normal, I will always get a 0 vector out. So this is basically just taking use of the geometric interpretation of the cross product. Nothing less, nothing more. And now I can calculate the cross products, nothing strange there, and we actually really end up with a single equation, and a simple equation, so that the ki incident field's amplitude of the wave vector times sine pi minus theta I must be equal to kr times sine of theta r. So I can just really calculate the cross products, and then I'm left out with this kind of equation. So that the amplitudes of the wave vectors, of course, they are equal, since the medium of interest is the same in both cases. It's the top side medium denoted with I, so that this implies that also the amplitudes of the wave vectors should be the same. So ki equals kr. And now essentially we have the condition that we have sine of theta I must be equal to sine of theta r, and this of course gives me the law of reflection, also known as the incidence angle theta I must be the same as the reflection angle theta r. So this was what we got from the first equality, and let's now do the law of refraction, so basically the Snell's law, and now we look into the former relations second second equality. So that's the latter equality here. And this gives me the way to derive the Snell's law. So now, essentially, I do not do the derivation anymore, but we are just basically playing around with dot products and vector products, and we end up with same kind of condition, but now it's slightly modified. So we have ki times sine of theta minus theta I. So this is what we have now left. So essentially it's the same as earlier. And now on the right hand side, we have kt times sine of pi minus theta t. And now the strange thing or new thing here is that the amplitudes of the wave vectors are now not equal. So ki is not kt. And how this is the case is that because we have 2 different media now of interest. We have the medium I and the medium T, and they are now optically different. And that gives me the fact that also the amplitudes of the wave vectors are different. So the amplitudes, now we can really link to the refractive indices of the media, and please, we can use the relations familiar already since the chapter 3 and 2. Ki equals to Ni, the refractive index of the medium I, times angular frequency times the speed of light, and of course the same thing for the Kt, but now we have the Nt there as the refractive index profile times omega divided by c. And now we can plug these into the equality of before, and we actually can find our Snell's law at the end. So we have Ni times sine of theta equal to Nt times sine of theta. So essentially we replace this with N omega c, and Kt we replace with Nt omega c, omegas and c's vanish, and sine pi minus theta I, essentially this is equal to sine of theta I. Please remember what was how sine is being defined, and the same thing here, so we are left with the Snell's law. That's quite nice. And now I'm done in 26 minutes. We have now the two equations of interest, and they hold for an interface between two dielectric media. So we now have verified the reflection law and the Snell's law, but this is the thing to remember here, that we have assumed that we have two dielectric media. We started with the Maxwell-Faraday, and this is what we ended up with. If you would need to do the same thing, for example, let's say an air-metal interface, then the boundary conditions and the continuity equations would be different. So please be warned, so that this is not always true, that it really depends on the materials of interest, but they do apply for the dielectrics. So this was my final warning. I'm done with this lecture, and please join me quickly when we are extending these into the Fresnel coefficients, so that we can actually quantitatively tell you how much light is being reflected and how much, on the other hand, is being transmitted when this kind of interface is nearby. I thank you for your patience and time, and bye-bye.